Hello, today we start Chapter 5, Integration. And actually we start the second big idea of calculus. In calculus there are two big ideas, differentiation and integration, and here is integration. We'll spend 3 days on 5.1, the idea of approximating area. Differentiation and integration are like two sides of the same coin. They're sort of opposite processes of each other, the yin and the yang of calculus. With differentiation, the problem is that given a function for the amount of something, we need to determine the instantaneous rate of change. Like the amount might be the position of an object. If I know its position at every time, then I can take a derivative and figure out its instantaneous velocity at any moment. That corresponds to a geometric problem. Given the graph of a function and a point on that graph, how do I find the slope of a tangent line? So the word problem for differentiation turns into a geometric problem. Now what about integration? Integration is kind of the opposite. Suppose I'm given a function that tells me the rate of something. Can I determine how much it changes over time? For example, suppose I know the rate of a car at various times. The car speeds up, the car slows down. From that information, can I recover the distance that the car has traveled? And it turns out that there is a corresponding geometric problem also for integration. Given the graph of a function, can I find the area under that graph? All right, well, let's see why that is the appropriate geometric question. Here's a nice little example. Imagine a toy car, so a little remote control car is moving along, and it moves in a very funny way. So for the first 2 seconds, it travels at a constant rate of 5 feet per second. And then over the course of 1 second, it travels exactly 15 feet per second. And then it goes 10 feet per second for 3 seconds and 5 feet per second for 2 seconds. How far has it traveled? Well, we can just take each of these 4 segments and do them individually. 5 feet per second for 2 seconds, just think about that, 5 feet per second, 2 seconds, you're going to go 10 feet. 15 feet per second for 1 second, 15 feet, and so on, and we can figure out the total amount traveled is 65 feet. But look at the graph. 5 feet per second for 2 seconds, that's really a y value times an x value. So 10 is the area of that rectangle. 15 feet per second for 1 second, I have a rectangle with height 15, width 1. The area of that rectangle is 15. The next rectangle has area 30. The last rectangle has area 10. The total area of these rectangles is 65. So it's the area under the graph that has given me the distance traveled. And you can imagine how this generalizes to non-constant velocities. Suppose my velocity is continuous. It starts at 5 feet per second and slowly increases to 15 and then decreases. That area under the curve ought to also represent distance. How do we get to that area? Here's maybe a more dramatic example. So, suppose over the course of 8 seconds, we know its speed over the course at various times, represented as constant values. We could split this section from 0 to 8 into more subintervals and find its velocity at more times, and do that splitting even further and further and further, and there's some kind of a limiting process where eventually I find the area under a nice smooth curve. So here is the area problem. Suppose my function f is continuous and positive on a closed interval from a to b. Over that interval, find the area below y equals f of x and above the x-axis. And it seems like we ought to be able to do that. If I know that this function really is 5 over x, and I want to find the area between 2 and 5, there ought to be some way to do that. And we will develop methods to compute this area exactly. But first, we will approximate the area, and approximating the area will lead us to a method for finding the exact area. So from this point on, for a little while, we're really going to focus on the geometric interpretation of the integration, but don't ever lose sight of the kind of information it's really giving us. If I know the velocity of an object over a certain amount of time, my goal is to recover distance traveled. Approximating area. There's one key method that we're always going to use, and it's called a Riemann sum. Now, Riemann sums mean that I'm going to use rectangles to approximate area. And there are three types of Riemann sums: a right, a left, and a midpoint Riemann sum. Let's make a right Riemann sum using 12 rectangles. So I want to approximate the area under this curve with 12 rectangles. So I'll take my x range from 0 to 12, and I'll split it into 12 equal width parts. These are going to make 12 tall, skinny rectangles. And now I need to decide how tall do I make each rectangle. And here's where the right comes in. For every rectangle base, I look at the right endpoint, and I follow it up until it hits the curve. And that makes the height of the rectangle. Let's take a look at the second rectangle, from 1 to 2. How tall should that rectangle be? I look at the right endpoint and follow the right endpoint up until it hits the curve. Then I can create my rectangle. Continuing on, how about the third rectangle? From 2 to 3, I follow the 3 up until it hits the curve and come across, and that makes my third rectangle. So the areas under these rectangles are approximating the area under the curve. And let's continue that process. There. Do you see how I did that? So for every rectangle, I follow the right side up until it hits the curve, and then that determines the height of the rectangle. Now, if you add up the total area of these 12 rectangles, it turns out you get 45. So, as an approximation for the total area under the curve, 45. Why not? That was the right Riemann sum. Let's take a look at the others real quick. How about a left Riemann sum? So a left Riemann sum using 6 rectangles. So the 6 tells me I need to take my span all the way from 0 to 12 and break that into 6 segments. So my rectangle bases will be divided at 0, 2, 4, 6, 8, 10, 12. And for each rectangle base, I will follow the left endpoint up until it hits the curve. So my base that goes from 2 to 4, I'll take the left side and follow the 2 up until it hits the curve, and that determines the height of the rectangle that spans from 2 to 4. And I'll continue this process as well. See if you can follow along with me. There, we've made our left Riemann sum using 6 rectangles. These rectangles have heights 1, 6, 2, 5, 4, and 3. And it's tempting to just add 1 plus 6 plus 2 plus 5 plus 4 plus 3 in order to get the area. But you would be so wrong if you did that, because what would you be forgetting? You'd be forgetting to multiply times the width. So to get the total area, it's 1 times 2, 6 times 2, 2 times 2, 5 times 2, 4 times 2, 3 times 2, and the total area you get is 42. Right, so in the previous example we got an area of 45. In this example we got an area of 42. Yeah, they're not far from each other. They are just approximations. One last example, how about the midpoint Riemann sum? So 6 rectangles again, so I'll split my rectangle bases, so the rectangle bases will each have length 2. And now I follow the midpoint of each interval up. So where does the 1 hit? Right at 5. That is going to be the height of my first rectangle. And for my second rectangle, I follow the 3 up. 3 hits the curve there, come across, and we can continue in this manner. All right, So the midpoint Riemann sum ends up giving us a total area of 48. Again, kind of similar to the others, and it's all just an approximation. People often like the midpoint Riemann sum because each rectangle gives a little bit of an over approximation and under approximation. Part of it lies over the curve and part of it lies under the curve. So in general, it makes a pretty decent approximation. Okay. Well, we aren't typically given pictures in order to make our Riemann sum approximations. More often, we are given formulas, an actual function that's defined, and based on that function definition, we want to figure out area under the curve. So let's approximate the area under y equals 1 minus x squared and above 0 to 1 using 5 right endpoint rectangles. So this right Riemann sum using 5 rectangles. So what's the first step? Let's divide my interval from 0 to 1 into 5 subintervals. So there we have it, 0, 0.2, 0.4, 0.6, 0.8, and 0.1. And incidentally, these points are called grid points, sort of where the dividing points between the rectangles, including the two very endpoints. Those are my grid points. And now I want the right endpoint rectangles, so I will evaluate my function at the right endpoints of each subinterval. So f of 0.2 turns out to be 0.96. I've drawn the height there on the right. And this is just something to plug into your calculator. F of 0.4 is 0.84. F of 0.6 is 0.64. F of 0.8 is 0.36. And f of 1 is 0. This is kind of funny. It'll give us a rectangle with height 0. And these values are the heights of the rectangles formed above each subinterval. So height of 0.96, height of 0.84, height of 0.64, height of 0.36, and a height of 0. And so the total area of all these rectangles is going to be calculated by computing height times width, height times width, height times width, height times width, height times width for each of those rectangles. And it turns out that that area is 0.56. So is this a good approximation? It's okay. It's not great. It would be better instead of using 5 intervals if I used 10 intervals. That would give me a better approximation. Or if I used 1,000 intervals, that would give me a very good approximation. We can do 5 by hand, but we could also get a computer to do 5,000 intervals pretty easily. Is this an over approximation or an under approximation? Definitely an under approximation. And you can see that whenever I have a decreasing function and I use right endpoint rectangles, I'll have an under approximation. One more example. Let's approximate the area under the natural log of x and above the interval from 1 to 7 using 3 midpoint rectangles. So the first step is to identify my grid points. What are the dividing lines between the rectangles? All of my rectangles have width 2. Oh, and here's a little calculation that we're going to see often. In order to figure out the width of our rectangles, I take the difference of the two endpoints, so 7 minus 1 in this case, and I'll divide by the number of rectangles. I have 3 rectangles, and that will automatically tell me the width of each individual rectangle. Grid points, I've identified 1, 3, 5, 7, but where do I want to evaluate the log? I want to evaluate at 2, 4, and 6 because those are my midpoints. So the rectangle heights are going to be natural log of 2, natural log of 4, and natural log of 6. Of course, every rectangle has width 2, so height times width, height times width, height times width. You add those together and you get a total of 7.74. A decent approximation for the area below natural log of x between 1 and 7. And again, you can see that this midpoint rectangle approximation is kind of nice in that it corrects itself a little bit with some over approximation and under approximation. Okay, I have said enough for this day one on 5.1. Give the worksheet problems a try. Don't neglect those. Think about what it says. Check your work. The answers are online as well. And ask me as you have questions. Good luck.